Hello everybody. It seems not so many students are listening just now. Yeah, altogether 3. Okay, so now we continue our studies of geometry of curves, and we look at the case n equals to 3. So curves in usual 3-dimensional space. So let me draw a picture. So we have somewhere the origin, and we have a coordinate frame, and we have a curve r of t. We can think about this curve as a trajectory of a movement of a particle, right? And now we want to associate a suitable frame, which is very useful for many purposes. Associate a frame with each point. So you see, there is a standard coordinate frame which is suitable to represent every point of our space. But if we look at a movement of a particle along a curve, then it is more convenient to associate a special frame. And to start with, we choose the first vector to be tangent vector. So let it be here, right? That is a tangent, right? And how we defined tangent vector? Tangent vector was defined as limit of this ratio, which is nothing else but derivative of vector function at a point t0. Of course, this is not a tangent vector. And by the way, what is physical meaning of this vector? If r represent the trajectory, then there is a natural physical sense. Namely, this is velocity. Velocity vector. So because of velocity, we may, somebody answered my question. Velocity vector. And we may also denote it by v. But if we are talking about frame, we have to choose unit vector. This unit vector, because of tangent vector, so the unit tangent vector. So what is it? We denote it by t, and that is, in terms of our v, we can divide by the length. For arbitrary smooth curve, as we know, this derivative is not 0, so we have no problem with computing this vector of the unit length. And also remember that for the choice, if t is s, arc length parameter, then what can be done? arc length parameter. If t equals to s, then we can also define it as derivative, okay, at s naught, right? So if t is s, natural parameter, then as we know, the derivative has unit length, because there was a lemma of which lemma, I don't remember number of that lemma, not the last, before the last. During former lecture there was a lemma that parameter of a curve is arc length parameter if and only if derivative with respect to this parameter has unit length. So we have several representations of the unit tangent vector, and also what differentiation definition. Look, differentiation definition. Differentiation definition gives us the following representation. R at t naught plus r prime at t naught times t minus t naught plus little o of t minus t naught as t tends to t naught. And the best is to look at arc length parameter. So for arc length parameter, I'll rewrite it as follows: r at s naught plus d over ds r at s naught times s minus s naught plus little o s minus s naught as s tends to s naught. So here I wrote the definition for arbitrary parameter, and here in the particular case of arc length parameter, of course it's the same as you see, right? Just up to notation t equals to s. But look, what is it? If we forget about little o, what is it? This equality, oh, I forget to put vector here and also over there. If you look at this equality, this is nothing else but vector representation for tangent line. So it means that difference between the vector of our curve, right? Difference between vector of our curve and the vector of tangent line is little o of s minus s naught in first degree. So tangent line is the first order approximation of r of s, also r of t, of course. The same is true for arbitrary parameter, doesn't matter. So you see, if we look at approximation for arbitrary curve up to quantities of the first order, right? Then the first order approximation is nothing else but the tangent line. So if we forget about all terms which powers greater than 1, then we obtain just tangent line, right? That is approximation by a line. So roughly speaking, at every moment, the movement is along the line, right? Up to little o of s minus s naught. Okay. It was about the very first vector of our frame. Now, the question is, okay, we had only first order, right? What's about second order? And now it will be a theorem. Number is 3, I guess, right? And that is the second order approximation of a curve. So if r of t is, sorry, not r of t, r of s is twice differentiable curve with the arc length parameter s at s naught and second derivative at s naught is not 0, then r of s minus rho of s is little o of s minus s naught as s tends to s naught, where rho of s is the vector, is not the vector, just the circle with center, okay, center is r of s naught plus 1 over kappa. Okay, kappa, I'll write like that. Kappa, Greek letter kappa, times n radius 1 over same kappa, which belongs to the plane phi, that is r over s naught plus alpha t plus beta n alpha beta are real. And now there are many notations like kappa n, so let me write all of them. Okay, t was written, first derivative, right? Then where rho is, yeah, kappa, let me write like that. Kappa is the length of second derivative and n is normalized second derivative so you see, when we discussed the first order approximation, okay, that's all. When we discussed the first order approximation, what happened? We looked at what happens with curve if we forget all terms of order greater than 1. S minus S naught, power 2, and so on, we forget about them. We don't care, right? That is how we obtain the first order approximation. And the first order approximation to arbitrary curve in the space is nothing else but the tangent line. And it gives the first vector for our frame, T, unit tangent vector. Now we want to understand what is the second approximation, right? And it turns out that if we, oh, sorry, very big mistake. Squared, of course. Squared. Very big mistake, of course. I was talking about second order approximation and I forget about this second order. Yeah? So now we look at what happens with arbitrary curve if we forget about all terms as powers of S minus S naught of orders greater than 2, right? And then it turns out that if we forget about all terms with powers greater than 2, then we obtain a circle. And now let us make, before the proof, several definitions, because all vectors which appear here, everything, circle and so on, they have special names. So, definition. Vector n is called the unit principal normal. So, I'll omit the word principal, just the unit normal instead of that. Principal normal. Kappa is the curvature. Rho of S is the osculatory circle, and pi is osculating plane. So you see, the curve is in space, so it might be the movement need not to be in a plane, right? Nevertheless, if we look at the movement up to second order, right? So if you forget about second order quantities of second order powers of S minus S naught, not second order, sorry, powers greater than 2, right? If you forget about powers greater than 2 of S minus S naught, then what happens? It turns out that you can think about movement along a curve as a movement along a circle. And this circle is in a special plane. This plane is osculate. Okay, so you see, look, what appears? It appears that we have a vector, that is, and that is the second vector of our frame, in fact. It is orthogonal. Why? Because the lemma before the last from former lecture said that if a vector has a constant length, then the derivative of this vector is orthogonal to this vector. It was lemma, I don't remember precise number, 3 or before the last. The last lemma was number 4, so lemma 3. So lemma 3 says that if, because derivative has the length 1, right? If we are talking about arc length, then derivative has a length 1. And so second derivative is orthogonal to this vector. So Lemma said if we have a vector with constant, is smooth curve. Let me smooth curve. Yeah, I should insert it. And yeah, otherwise it is not correct. And twice differentiable with at S naught. So you see, smooth curve not only in S naught, of course. So the first derivative should be defined everywhere and should be non-zero everywhere, right? But the theorem is local because it says only about the behavior of the curve near the point S naught, right? But nevertheless, we need something global because, of course, the lemma is valid only for smooth curves. Yeah. Some global behavior should be satisfied as well, right? So, look. So, second derivative is orthogonal, right? That is why it is called normal, because it's orthogonal to tangent. So here, those vectors are orthogonal. And the plane which is generated by those two vectors is osculating plane. So up to second order quantities, we can think about movement along such a curve as a movement in the plane, right? Although the curve is in the space. Okay, now proof. First of all, we use Taylor formula for components. It gives, look, so we look for components of R of S. So we have vector function, right? And each component is a usual function, so we can apply Taylor formula for each of components. And it gives us the following representation. So R of S naught plus, or maybe instead of S naught plus delta S, I'll write just S. R of S equals to R at S naught plus d over ds R at S naught times S minus S naught plus 1/2 d over ds twice S naught times S minus S naught twice plus little o of S minus S naught squared as S tends to S naught. Right? So how we obtain this Taylor formula? We write Taylor formula for each of components and then put them together into vector form. Okay? It gives such a representation. Taylor formula, of course, with piano form of remainder, right? Piano form of remainder. Okay. Now, let us compute what is R of S minus, so minus center, R at S naught plus 1 over kappa n. So what is it? What is this vector? Let me write it in details. Yeah. So if we substitute what we obtain, that is d over ds R at S naught times S minus S naught plus 1/2 d2 over ds twice R at S naught times S minus S naught squared plus little o S minus S naught squared minus 1 over 1 over kappa squared times d2 over ds twice R at S naught. Yeah. So I wrote such a difference between vectors, right? And then let us think, let us collect everything what we have. Okay. So we have d over ds R over S naught times S minus S naught plus, and then this vector has a common multiplier of this form. Yeah, plus little o of S minus S naught squared. Yeah, that's it. Okay. Okay. Now, recall, I want to prove that R of S is roughly speaking circle up to quantities of order greater than 2, right? Hence, I need to, first of all, let us check that indeed we have the length of this vector is constant up to quantities of order 2. And maybe I should indicate also this little o is vector. This vector, right? Because remember, I applied Taylor formula for components, right? So each component has its own Taylor formula, right? With its own little o. For each component, we have little o, right? Then, now look, we have two orthogonal vectors, right? Hence, there is a third vector which is orthogonal to each of them, right? For a while, I don't want to call this vector somehow. Later, it will be called specially. For a while, this is just a third vector, right? And now, let us compute the length of our vector. The length of a vector in three-dimensional space, if we have orthogonal frame, right, orthogonal basis, Tn and third vector, then the length can be computed as square root of sum of squares of coordinates, right? Now look, what is it? That is T, right? And yeah, also this is that is n times kappa, right? Because look how we defined n. n 1 over kappa times the second derivative. So second derivative is nothing else but that one. So you see, first vector of our base, right? Second vector, and also there is a third one, right? But it is not explicitly here. But so what is first coordinate? First coordinate is coefficient in T. Coefficient in T is, look, S minus S naught, right? Plus, also there is a component here, right? So I don't know why, which I'll denote it like that, right? Component with respect to vector T of S minus S naught squared plus yeah, plus. Now, what is component here? Kappa times S minus S naught squared over 2 minus 1 over kappa squared. Yeah, that is the coefficient in n, right? Plus, also there is a component here. I'll denote it or n of S minus S naught squared also plus third component. Okay, I think I should denote it. So I'll denote it by B without name yet. And plus little ob of S minus S naught squared, also squared. That's it, under square root everything, right? Everything is under square root. Okay. Now, let us compute what we have under square root. Remember, I am interested only in terms of order up to 2, right? All terms which contain greater powers of s minus s naught than 2 will be in little o, right? Okay, then what we have here? Look, if I take square of this term, then how to compute this square? Square of the first, square of second, and double product, right? Double product, s minus s naught times something with larger powers than 2 will contain larger powers than 2, right? Square of this term also contains larger powers than 2, right? So altogether, only s minus s naught squared is interested for us. Next, now square of this huge expression. So what we have here? Of course, double product of little o times something will be also little o. Square of little o will be also little o of this square. The only thing which is not little o is square of the first. Square of the first. Square kappa squared, right? Kappa squared times what? Square of this is power 4, right? We don't care. Power 4 is greater than 2. Little o of power 2. So double product. Now double product with minus 2 times s minus s naught squared over 2 times 1 over kappa squared. Wow, it's a break. And also square of second plus 1 over kappa 4. Yeah. Plus little o of little o of which powers? Yeah, of s minus s naught squared. Yeah. So now this is not a vector, right? I collect all those little o. Now look, what is here? Minus s minus s naught squared. So we cancel this. And what remains? Just 1 over kappa squared square root. So we obtain 1 over kappa. And then we may use Taylor formula for square root. 1 plus something to obtain. It can be written like that. So you see, the length of this vector is constant up to quantities of order greater than 2. Okay, let's have a break. So you see, we computed the length of this difference, right? And this length is, roughly speaking, constant, right? It's constant up to something, right? We know that if, in general, right, what is circle? It's something, is the set of points which are placed on the same distance from one point in a plane, right? So it suggests that indeed we have a circle, right? But it doesn't prove it. This is only suggestion. This is only suggestion. So let us understand what is the circle precisely. So to do it, firstly, maybe I could add it also to main definitions. So that is an addition to definition. You may write it just now, new definition. I'll write it here. So R, which is 1 over kappa, is the radius of curvature. So that is abbreviation of, instead of that we could say radius of circle of curvature, right? Or osculating circle, but radius of curvature, that is shortest. Okay, so let me try to compute. First of all, what is vector equation? Vector equation for a circle with center at the origin. At the origin, that is just, in fact, there are many possibilities. Let me choose like that, cosine phi, let it be I plus r sine phi j. So don't ask me why minus r cosine and r sine. Usually we write r cosine plus r sine, right? Why minus r cosine and r sine phi? You will see a little bit later, because this is suitable for our purposes. But of course, that is a parametric equation or vector equation for a circle, right? With center at the origin and of radius r, right? Radius r. Okay, now look. So osculating circle then how to obtain the equation for the osculating circle in terms of this phi. So we need to translate the center, right? The center of our circle from the origin to special point. Which point? Where is center of our circle? That is, right? So it means what we should do, and also what we should do, we should choose vectors I and j. You see, instead of I and j, I should take t and n, unit tangent and unit normal. And now j I'll take as unit tangent, and I unit normal, principal normal, right? That is how it will be more suitable for us. So now osculating circle will be R of S naught, so plus R sine phi t plus, look, so n, right? 1 over kappa. 1 over kappa is nothing else but R. So plus R times 1 minus cosine phi n. That is precisely an equation for osculating circle in terms of parameter phi. Now, suitable choice of phi will be S minus S naught over R. Then, look, osculating circle rho of S will be R of S naught plus R times sine S minus S naught over R t plus R times 1 minus cosine S minus S naught over R times n. That is precise equation for our osculating circle, right? Osculatory. Oh, osculatory, I said. Osculatory. But maybe I was wrong. Okay. So, but now remember, we are interested in an expansion in powers of S minus S naught. So remember Taylor or Maclaurin formulas for sine and cosine. If we remember those formulas, then how we may write it? So R times S minus S naught over R t plus here R times 1 minus S minus S naught squared over R squared also 2 times. Yeah. And of course some vector of S minus S naught squared as S tends to S naught. So I took, that is cosine, representation of cosine, right? Representation of cosine. That is representation of sine. Sine is equivalent to its argument. And, of course, up to quantities of order greater than 2. Look, 1 is cancelled. Then here we have plus, right? Also R is cancelled. Here R is cancelled. And now compare this with our expression for R of S. R of S naught. Then that is precisely T, right? Precisely T. T is this. Then plus 1/2. And what is second derivative? Just kappa n. And kappa is precisely 1 over R times n. So you see, this expression is the same as that one. And then theorem is proved. Because, once again, so T is d over ds. And second derivative is kappa times n, or in other words, 1 over R times n. And that is precisely the same. And then theorem is proved. Okay. Now, you see, the curvature was defined. The curvature was defined. Yeah. Curvature was defined for the arc length parameter only, right? Osculating circle. Which? That one. I moved. So here the circle we center at the origin. Now I added the center. The center is here. The center is here. 1 over kappa is just r times n. So r times n plus r of s naught. That was added to the origin. Okay. Okay. Now, look. So we know how to compute curvature in terms of the arc length parameter. But usually we have just an equation for the curve, right? So the question how to compute the curvature if we don't know the arc length parameter. Of course, you can find this arc length parameter, and then you will obtain the expression which you are interested in. But it's better to find the expression explicitly. So let me write it here. Theorem 4. Theorem 4. Computation of curvature. So if r of t is twice differentiable curve with but in fact I think no, I think I don't need to make this supposition about just twice differentiable curve. Then kappa equals to the length of vector product first derivative times second derivative divided by cube of smooth, of course, smooth is smooth twice differentiable curve. Twice differentiable does not imply smoothness. Smooth means this derivative is not zero, right? That is necessary, of course. Proof. So what is kappa? By definition, kappa is that one. And let me firstly to recall how we computed d over ds of r of s, right? It was computed, in fact, let me recall this representation for the unit tangent vector, but now once again let me obtain it with the help of the chain rule. So that is d over dt, right, of, I'll write like that without argument, just derivative with respect to s is d over t of r times dt over ds. That is the chain rule, right? Chain rule. And then I can write it as dr over dt over ds over dt. And that is precisely ds over dt is nothing else but model of r prime. It was in theorem 2 about the length of the curve. That s prime equals to the length of r prime t. So s prime of t equals to r prime of t. It was theorem 2, right? So that is how that formula was obtained also, right? Now, look, this is very good rule, in fact, which says that we can obtain derivative of arbitrary vector, not especially r, because instead of r I can substitute here arbitrary vector function, right? So now I need to compute second derivative. Second derivative is the derivative of the first, right? So it follows that second derivative of r is equal to d over dt of the first derivative over that is r prime of t, s prime, which is length of r prime. Now remember, here I differentiate the first derivative, but the first derivative was computed before, right? So I need, okay, I'll write r prime of t times now derivative of r prime of t over the length prime. So you see, prime denotes derivative with respect to t. Derivative with respect to s is always written like that, d over ds, right? Prime is instead of derivative with respect to t. Okay, then what is it? We differentiate ratio, right? So, or better to say, product of vector by constant 1 over this length. That is better. We had a rule how to differentiate it, so it gives 1 over r prime of t squared times r double prime of t minus 1 over r prime remains, then derivative of this, in fact it will be, we have this, then we differentiate 1 over this modular. 1 over this modular, how to differentiate? Minus 1 over squared, so altogether we have cube, then times derivative of, I'll write it here, of this modular, right, times r prime and t. Now, curvature itself. So the length of a vector. How we may compute it? Now, with the help of vector product, we need vector product, right? Not scalar product, I'm sorry. Vector product. How to compute it? The idea is the following. So we can write as vector product d over ds r times second derivative. Why? Because remember what is vector product. Vector product equals to length of vector product. Length of vector product. What is length of vector product? It's product of lengths, right, times sine of the angle between vectors, right? Now, remember, product of lengths. Length of this times length of that. Length of that is 1, right? Because what is? Yeah. Where it was? It was somewhere. dr over ds. No. Yeah. dr over ds is unit tangent vector. So the length is 1, right? Length is 1. And now what's about angle between those vectors? I refer to lemma 4, right? Lemma 4 says if a vector has a constant length, then derivative is orthogonal. So angle is pi over 2. Sine is 1, right? Then, indeed, we have this equality, right? Length 1, angle pi over 2. Right? Now look. We have vector product of this vector times ds over dr. ds over dr, sorry, dr over ds is vector r prime times some constant, right? So when we multiply r prime vector product times r prime, we obtain 0, right? So it means when we compute this vector product, when we substitute here this expression, right, we can forget about second term because vector product gives 0. So we are interested only vector product to the first one. Okay, then what we obtain? So dr over ds is 1 over r prime, length of r prime times r prime, right? And here, once again, I forget about t, r prime squared times r double prime. Of course, constants may be taken outside of vector product and then outside of the length, right? So altogether, what we have, precisely vector product of r prime times r double prime over r prime cube. What we have to prove, right? Okay, so theorem is proved, and corollaries, in fact, many corollaries. First, explicit formula. So if r of t, x of t y of t, z of t. Then what is curvature? Curvature is equal to length of this vector I, j, k, x prime, y prime, z prime, x double prime, y double prime, z double prime over x prime squared plus y prime squared plus z prime squared 3 over 2. Here I wrote vector product r prime, r double prime. Here the length cubed. Second, z equals to 0, plane curve. If we have plane curve, then what happens? Look, these are zeros, right? 0, 0. What remains? Kappa is equal to modulo of. So only one component is not 0. K component. We have this determinant. It gives x prime y double prime minus x double prime y prime over. Here practically the same, that prime is 0. So x prime squared plus y prime squared 3 over 2. That is for plane curve. Third, y equals to f of x. If we are interested in curvature of the graph of a function, then what happens? There is a particular case when t equals to x. T equals to x. Our parameter t equals to x. Then x prime is 1, x double prime is 0. Because x equals to t. X prime is 1, x double prime is 0, right? So what remains? We have just y double prime over, and here we have 1 plus y prime squared 3 over 2. That is curvature of a graph of a function, right? Now I can define the next definition. B equals to t n is called a binormal. The frame T and B is called T and B frame or Frenet frame. Frenet frame. Also, special names for planes. So you see, we have osculating plane, right, which contains T and N. So osculating plane, T, N. here I write generating vectors for that plane, right? That is osculating plane, right? Then normal plane. Normal plane, of course, is orthogonal to T. So it means generated by N and B. And also, third plane is called rectifying plane. That is orthogonal to T and B. Also, Frenet frame, instead of Frenet frame, you may talk about Frenet but I didn't see in English, in fact. I didn't see in English. In English only frame, Frenet frame, TNB frame. So TNB frame moves together with the point if you move along a curve. Okay, now the interesting story is to look at the variation of those Frenet frame vectors. Look at derivative with respect to S of B. So binomial vector, how it varies with respect to arc length parameter, which is most natural. So by definition, we need to differentiate this vector product. We know how to differentiate vector product, so that is, we differentiate the first dt over ds times n plus dt times dn over ds. Okay, t, recall, is, what is it? Yeah, t was dr over ds, right? So that is second derivative. Second derivative of r with respect to s twice. And what is n? It's here. So times 1 over kappa times same vector. What can you say about this vector product? If you consider vector product of a vector times itself up to a square, it's 0, right? Vector product is 0. That is 0. Plus, okay, what is here then? Look, what we have here, n is a vector of constant length, unit vector, right? By lemma 4, it is derivative is orthogonal to this n, right? So this vector is orthogonal to n. So this vector belongs to rectifying plane, in the plane which generated by vectors t and b. Hence, I can write it as, let's say, alpha t plus beta b, right? Beta b. So, once again, vector product t times t gives what? 0, right? So what remains? Vector product t times b. T times b, what is it? Vector product t times b is nothing else but, in fact, minus n, right? And it explains why, you see. So what remains? Only some coefficient times n, right? And we call this coefficient minus tau times n. Tau is this coefficient, just minus tau. And tau, definition, tau is called a torsion of the curve. Nah. And it seems I have no time to compute it. Just a couple words. In fact, torsion and curvature together, they determine the curve completely. If you know torsion and curvature at arbitrary moment, then you can reconstruct the shape of the curve. I'll not prove it. That is done in more general courses of differential geometry, but nevertheless, still I have to do something with it. But for next time, poof, very slow, very slow. Okay, thank you for your attention.